BGP Part 2, Understanding BGP Attributes. Now, I'm sure you're wondering what that frog is on the screen, and, well, let me explain. My younger brother is into this game called EverQuest, where you create these characters, and each one of these characters have all these attributes about them. You have to give them certain amounts of stamina and strength, and they have, wizard power or whatever it is. I'm not too sure what all that entails, but based on these attributes, you give this character, which looks like a mean-looking frog there, is pretty much how your character will react and kind of its strengths and weaknesses and so on. And BGP is the same way. Every route that comes into your BGP routing table has specific attributes, and you as the administrator get to control those attributes and dictate what attributes will be the best route selection so that you can have the best route available for you. Now, this is very similar to all the other routing protocols that we've talked about, like OSPF and RIP. It's just OSPF and RIP have things like simple attributes where we have bandwidth or hop count, a single attribute that's helped select the route. BGP is so flexible that we're going to go through an entire nugget just talking about all the different types of attributes that we have to manipulate our routing tables. And then finally, we will, on the last section of this nugget, we will say, okay, how do all these attributes come together so that your router is able to pick the best possible route? Now, before we start getting into individual attributes and how they can affect your routing table, let's look at the broad categories of BGP attributes. The first thing that we see here is, as I mentioned, BGP calculates its metric, the best way around the network, through this whole series of attributes. And there are two broad categories of attributes with, I guess you could say, four subcategories of those. The first two that we see is well-known and optional attributes. Well-known attributes are the ones that have to be supported by every router that claims to be BGP compatible or support the BGP routing protocol. I guess you could say that in order to support BGP, you have to support these well-known attributes. Under that category, you see two subcategories, and those are mandatory and discretionary attributes. Mandatory attributes, I abbreviated that with MAN. Mandatory attributes are ones that must be included in every single BGP routing update. Discretionary attributes, on the other hand, is up to the router and up to you as the administrator whether or not you want to have those attributes in there. Now, in the optional category, optional does not have to be supported by all router manufacturers. You might create your own router and decide, you know what, I want to support BGP, but I don't want to support some of these optional attributes because either maybe I don't see value in them, or it takes too much to implement on there, or maybe you want some optional attributes of your own because you want to develop your own proprietary system. That's what you'll see in a lot of attributes that are optional, is a lot of vendors' proprietary BGP manipulation methods. Now, under that category, we have transitive and non-transitive optional attributes. Transitive are the ones that will continue traveling through a system regardless of whether or not they are recognized by a BGP router. A non-transitive optional attribute is an attribute that will be stripped off by a router if it does not understand it, or it just chooses to not propagate that attribute. Now, underneath, I kind of listed all the attributes. I'm not going to give you a description now because, hey, that's what the rest of this nugget is going to be all about. It's talking about each one of these, and I put a little marking next to it telling you whether that is a mandatory, discretionary, transitive, or non-transitive attribute. So it's a great page to use as reference. Here we go. We're going to take each one of these attributes one at a time, starting with the AS path attribute. Now, this is a mandatory, well-known attribute. It has to be in every single routing update. And what it is the path that a route has traveled. Now, initially, when you insert that route into the routing table, we'll say an autonomous system 100, it has an empty AS path. It hasn't left any autonomous system yet. Now, as it leaves this autonomous system, let me get my freehand drawing tool. As it leaves this system, it's going to have the AS number prepended. And I put that in red, prepended, because it will tack it onto the front. And if you don't know that, because it's kind of counterintuitive in how that works, but if you don't know that, you might look at some of these paths and get backwards pretty much to the list. So as it leaves the system, we'll say the AS path is currently 100. It comes into this system, and it's 100 as it goes into that system. But as it leaves this system, what do you think it becomes? 100, 200. Prepended. It's added to the front of those advertisements. Goes into this one, and by the time it reaches this system down here, the AS path looks like 100. Oh, see, I did it backwards. I'll do it from the right. 100, 200, 300. Each autonomous system that it crosses adds its autonomous system number to the front of it. Now, initially, and I mentioned this early on in the concept nugget on BGP, initially, this is the route selection criteria that routers will use to figure out the best way around the network. As the route comes in here, it will have an AS path of 400, 100, kind of starting in 100, going to 400. And it will look at that and say, okay, that has this shorter AS path. It's 2 AS hops instead of 3 AS hops, so that will be my preferred way. But our goal is to prevent it from using AS hops, because how reliable is that? It factors in no other real criteria other than how many autonomous systems it passed through. This is also a simple but ingenious method of loop prevention. There are tons of loops on the internet because it's a spider web of network connections. I mean, just look at this one right here. We would have that 80.0.0 network coming through and all the way back to autonomous system 100. Now, this is an ingenious way of loop prevention because autonomous system will look at the AS path and go, oh, hey, look at that. I'm in the AS path. That means that is a looping route and I will not accept it. That is the loop prevention mechanism of the entire internet, and its beauty is in its simplicity. So the AS path attribute is pretty critical, but nowhere near as critical as the next hop attribute. This again is another mandatory, well-known attribute. It has to be in every routing update, and of course it indicates, wow, the next hop IP address to get to that network. So let's say that this router down here was advertising 80.0.0 or whatever network. It's going to come out of this interface and go to this eBGP neighbor. And that will typically be the IP address of the sending router. So it will say, okay, I now know about the 80.0.0.0 network, and the next hop to get there is this guy, 150.20.31.5. That would be the next hop attribute. And then once this router sends that attribute up and over to this router up here, the next hop would typically become that one, 147.23.91.1. That will be the next hop that I use from this router to get to the 80.0.0.0 network. Pretty simple, right? Well, it seems simple until you get to things like this, the next hop on a shared media network. Now, okay, I have to confess, it's pretty rare that we have autonomous system boundaries on Ethernet networks. Although now that I think of it, it probably won't be rare for much longer with things like Metro Ethernet evolving in our industry. However, here's the concept. If a receiving router is on the same subnet, the next hop remains the same. And let me explain that using this diagram right here. We have 3 routers in 3 different autonomous systems. And let's say our eBGP relationships look something like this. These 2 routers are neighbors, and these 2 routers are neighbors. So these 2 do not have direct neighbor relationships. Now this next hop, I'll call it a feature, is actually kind of handy in this case. Let's say behind this network we have, I'll just say 20.0.0.0. And it advertises, because it has a neighbor relationship right here, it advertises, hey, I've got the 20 network. Now the next hop IP address will be 10.0.1.3. So this router will say, great, I now know about the 20 network. I'm going to tell my neighbor down here, hey, I know about the 20 network. But what is the next hop? Well, because of this rule, because of the shared media and all these being on the same subnet, the next hop will still be 10.0.1.3. It will still point to that same IP address. BGP does that for us, and it's a good thing in this case because this router doesn't have to go boink off of that router to get over here. It can just go straight to that router's IP address since the next hop did not change, and that's a more efficient route. But this concept can cause problems when we start looking at NBMA multi-point networks. Now, if you've gone through the advanced wide area network configuration and started looking at the frame relay nuggets before, you already know my opinion on NBMA multi-point networks. I loathe them. However, you may encounter them when you're sitting in the CCIE lab. Here's the concept and the problem that it creates. Look at our network. It's a multi-point network. You see the IP addresses are all in the same subnet. However, all the routers are not directly connected. It looks like a single subnet Ethernet style networks, but these two routers right here do not have a direct PVC connection. This router down here has to go through this router to get to this one up here. So same scenario. The 20 network is advertised from this router down to here, and it hits this guy, and it says, okay, I now know how to get to the 20 network, next hop being this one right here. I'm going to advertise that out to my neighbor down here so it knows about the 20 network, but what will the next hop IP address be? Notice I emphasize next hop. This one right here. But is that really the next hop IP address? No, it's not. It's the second hop IP address. This router has to go to this one next, and then this one will allow it to go over here. That will cause a major problem in our routing. Now, there are ways to fix it. My personal preferred way is to convert this to a good point-to-point frame relay topology, to where each one of these is a point-to-point link. That will fix the problem in and of itself, because this rule will no longer apply. It's no longer seen as shared media at that point. But if you must keep this as a multi-point network, we can start tweaking the BGP attributes, and we'll get into that when we get into the configuration of BGP, to allow this scenario to work correctly. The final well-known mandatory attribute, the one that has to be in every single update, is the origin. Where did this route come from? We need to know. It can be one of three values, which in my personal opinion is not flexible enough, but this is how the standard was written. The first one is IGP, as in the route originated from an interior gateway protocol of some sort. The second one is EGP, which is the exterior gateway protocol. Now, you may remember in the BGP theory nugget, I emphasized that EGP is not BGP. BGP does not fall under the umbrella of EGP. EGP is the old version, as in before the 1990s version of BGP that was used around the internet. Now, my question to you is, who's using EGP anymore? The answer is nobody. There's nobody that uses EGP. So if you ever see a route originated by EGP, somebody's probably messing with you, and somebody's changing the tags on their route to look like it originated from that, because nowadays nothing originates from that protocol. Finally is unknown, as in BGP has no idea where this route came from, and it's shown in the routing table with a little question mark. Now, I will tell you that most of your routes in BGP will probably show up as unknown. The reason why is anytime you redistribute a route into BGP, maybe you take some of your internal networks and redistribute them into the BGP routing protocol, it instantly goes to an unknown origin unless you manually tweak that. IGP only shows up if you use specific methods, primarily the network command, to get routes into the routing table of BGP. So most of the routes will have an origin of a question mark as unknown. Now we get into some of the well-known optional attributes. These will be supported by any vendor claiming to support BGP. However, you don't have to use them. But these are the ones that I think give you the most control over your updates. First off, the local preference. Let's say that you have redundant service provider connections, and we'll say up here is service provider B, and on the left is service provider A. So we have our two different service providers that we're receiving the entire internet routing table from. Now, let's say for most of the routes, I want to prefer service provider A. They're my primary. But for some of the routes, and I will specify exactly which ones, I want to prefer service provider B. Well, you're going to get nearly identical routing tables coming in here because it's the same internet routing table. It's just you want to select certain routes to choose and tag as the preferred routes. So let's say you get the 20 network coming in from service provider A, and you also get the 20 network coming in from service provider B, but you want it to prefer service provider B for that one. So by the time it reaches this router down here, and maybe it sees the 20 network, you want it to go to this router as its next hop rather than this router. Well, local preference is your way of doing it, because both of these routers will advertise and say, hey, I've got the 20 network, and by default, this will choose whatever one has the shortest AS path number. So by setting the local preference higher, and I put little notes, higher is better in this case, it will prefer whichever one you mark as the higher local preference. So maybe coming in here, you say this has a local preference of 100. Now by default, everything has a local preference of 0. This will come down, this one will say, okay, I see the local preference of 100, I am going to prefer that way out of the network. Many people get local preference and weight confused. It's one of the things I've seen a lot of people stumble over in the past, and the reason why is they do nearly exactly the same thing. However, weight is specific to a local router. Check this out. We talked about local preference just a moment ago. Weight is a Cisco proprietary attribute. You notice it didn't make the list at the beginning. It doesn't really show up as optional or mandatory or anything like that because it only affects the local router. And this is the big difference between this and local preference. It gives you control of routes on the same router. Again, same scenario, service provider B and service provider A sitting up here. You're getting routes from both of them. This attribute allows you to, on this one router, choose which ones are more preferred. So if I get the 20 route over here and the 20 route over here, I can set the weight of service provider B to be higher. Again, this one is higher is better. I'll put HIB. Higher is better for this attribute. And we're going to see some attributes where lower is better. And this router will prefer the weight that is considered higher. Now we're going to see, because I know it's starting to already get twisted in some people's mind, because you might say, well, okay, if higher is better on weight and you set the weight of this one to be 100, but higher is better on local preference and you set the local preference to this one of 100, now you've got competing information, don't you? You have one that has a higher weight and one that has a higher local preference. Well, which one is going to be preferred when it all settles down and the dust settles on this router? Well, that is the job of the last slide of this nugget. I'm going to show you a major list of all the attributes and show you which ones win over one another. The big difference of the weight and the local preference is that the weight does not affect the routing policy of other routers. In the last slide, you saw that I had two routers connected to two different service providers, and they actually advertised in and affected the routing policy of this router right here. It received the local preference and it said, aha, this one has a better local preference, so I'm going to use that. Weight never does that, and that's why it's Cisco proprietary. Other routers don't need to support the weight. It only happens when this one goes up to this router and says, okay, I want to reach the 20 network. Now this router has to make the decision. Which 20 network do I prefer? That may be a job of the weight attribute. This one, I must confess, I do not use all the time. It is the atomic aggregate route. What it does is informs a router simply that a route has been summarized. In this case, you see on the screen I have 172.16.0.0. It's a private network, which isn't typical of BGP, but works for this example. This route will be sent from this router to this router. Now, maybe behind it, it has all these specific routes, 172.16.1.2.3, and so on, but it decided to summarize or aggregate all of those routes into a single advertisement. All the atomic aggregate does is tag that route and say, this is a summarized route, so the administrator on this router can look at it and go, oh, okay, well, there may be many more specific routes that make up that aggregate that I might not know about hidden behind that router. The multi-exit discriminator, or MED, also called the metric, you may hear it referred to as the metric of BGP, and don't let that confuse you, is the closest attribute you'll ever get to breaking the golden rule of BGP. What this attribute does is suggest, and I underlined it, I want to make sure I emphasize this, it suggests an entry point into your autonomous system. Let's say this bottom network is your autonomous system, and you have multiple entry points, 2 entry points that go to a single service provider connection up here, and you want to suggest to that service provider that they use this link over on the left-hand side rather than this link over on the right-hand side. And already you might have guessed that in the med or the metric, lower is better. Lower is better. Now, the easy way that I remember this, the easy way that I remember which one's lower and which one's higher, is that when you think of the two that have higher is better, local preference and weight, just think of those terms. If I'm thinking preferred or local preference, I think, the most preferred or the higher preferred is better. If I think of, the best weight, I'm thinking of more weight. A higher weight is preferred because I have more weight on that decision or more weight on that criteria. Now, on the multi-exit discriminator, or MED, also known as the metric, when I think of metric, I always think of routing protocols. And I think, oh, okay, the routing protocol with a lower metric, or the route with a lower metric, is the one that's preferred. Now, don't let that term confuse you of metric. A lot of people use that as slang for this attribute. And some people get it confused with metric as a broad statement, like the whole metric of BGP. The truth is, BGP doesn't have a whole metric. It just has a series of attributes that helps it pick the best route. So in this case, we are suggesting, now let me emphasize suggest, to this service provider what is the best way into our network. Now, what is the golden rule of BGP, as we talked about in the theory nugget? The golden rule says we can never tell another autonomous system how to route their traffic. Now, looking at this picture, it looks like we're telling another service provider, another autonomous system how to route their traffic. This is the key. We are suggesting to them how to route their traffic. It is their choice whether they will use our metric or not. And the truth is, by default, if they leave all their attributes by default, it will not use the metric to influence that choice, that decision that they make. So the service provider has to say, you know what? I will accept your suggestion and I will go this way. So like I said, this is the one that gets us the closest to breaking that golden rule, but doesn't quite get there. And the final 2 attributes. There are a ton of attributes. It's funny, when it makes you look at EIGRP and IGRP and you think, wow, they have 5 ways that you could use to influence their metric and their routing. And then you look at BGP and you think, never mind, this one beats them out. You have the aggregator and the community, and these are pretty short and sweet, so I grouped them on the same slide. The aggregator goes right along with the atomic aggregate. Atomic aggregate just tags a route and says this route is summarized. The aggregator attribute tells you who summarized that route. What IP address or what router summarized that route and performed summarization on the aggregated route. It's just that simple field is all that attribute is there for. And you might at this point start saying, well, it seems like we're getting almost minute and almost picky with these attributes. Why would I use that? Well, what you could do is, I mean, there's a whole plethora of scenarios that you could throw at this, but you could say, you know what? I don't want to accept summarized route from this aggregator if you have specific preference of who can send you summarized route. So again, it's just an attribute that you could choose to use in your route filtering. Now the community, I love the community, is used for route tagging, and you have this little box of crayons here. The community attribute saved my tail more times than I can remember when I was starting to figure out how to filter certain routes out in my BGP routing table. And you'll see as we start getting into all the BGP configuration, we're going to start having to say, all right, we don't want routes coming from this router, but maybe we want only certain routes to come from that router. So we can't block them all. We only have to block some, and we can't block them at certain points in our network. We're going to start seeing some really wildly complex scenarios. And the only way that we're going to be able to mark the routes that we want to filter out is by using a community attributes. We're going to see that there's some well-known communities and some not so well-known communities, communities that you can define customized for yourself, and you can use those tags to allow or filter routes out of your network. And finally, the route selection criteria directly from Cisco's website, because I couldn't write them that small and that neat. This is in priority list how a router chooses the best way to get around a network. So when it receives, let's say, let me just draw a router up here so we can have a visual with it. I have a router getting routes from two different sources, two different service providers. The first criteria that it uses is that it will always exclude routes with an inaccessible next hop. And that's a big one to remember. If you are not having routes showing up in your routing table and you think, oh my goodness, why aren't they there? And you start troubleshooting all these areas, that's the first thing that you should look at. Can I reach the next hop that is attached to those routes? Every route, I should say, will have a next hop attribute. Let's say this one's coming in and is saying, I have the 80 network, a Class A network, and the next hop that you're going to use to get there is 1.1.1.1. The first thing that you should look at is, can I reach? And if I do a show IP route, does 1.1.1.1 or some sort of subset of that network show up as reachable? Because if not, I will never see the 80 network in my routing table. After that, it now comes to our attributes. Prefer the highest weight. So weight rules over all. If I set a route coming into my router and I say the 80 route from this service provider has a highest weight, it immediately wins. That is the number one winning attribute. Number two is the highest local preference. So if your weights are identical, it will fail over and say, well, who has the higher local preference? If those are identical, it will prefer routes from that the router originated. So if your router originated a route, maybe let's say you have the 80 network right here, and you said, I am originating that advertisement, and then someone else comes in and says, well, wait a sec, I have the 80 network. You're going to prefer the one that you originate, and that just kind of makes sense. The one that's attached to you or that you originate will win. The fourth one, and this is the one that most people fall back on, is the shortest AS path. Only the length is compared. If you don't modify anything, typically these first three will all be tied. You will have equal weights, equal local preference. They will not be originated by you, rather they'll be originated by some other person. So you will fall back and choose the one that has the shortest AS path. Now if they have identical AS paths, equal in length, it will then go down and say who has the lower origin code, meaning that IGP is the most preferred. If you have a route and it's tagged with an origin of the Interior Gateway Protocol, it is the most preferred. Second preferred is EGP. I don't know why that is, but that's the way the RFC standard was written. And finally, you will prefer routes that have an incomplete origin. So those are the least preferred routes of that group. Now, if those are tied, as in the route has the same origin, it finally looks at the MED. That is the way that you can influence other autonomous systems that to have a preferred route into your network. So way down, number 6 on the list is your influence to other autonomous system. If those are equal, it then starts getting almost random at this point. The 7th is it's going to prefer external to internal routes. If those are equal, meaning they're both external or they're both internal, if those are equal, it will then choose the closest IGP neighbor if it's an IGP pack. For EGP, it will prefer the oldest, the one you've learned the longest. You see how random we're getting? It's just saying, you know what? Whatever one I've learned first. Now, if all of those are equal and it says, you know what? I learned these routes at exactly the same millisecond, which is a pretty rare chance, but they had to put one in there just in case that chance happened. Number 10 is it will prefer the paths from the router with the lowest BGP router ID. And at that point, you're just saying, you know what? Whoever has the lower name, maybe you have one router that has a BGP router ID of 10.1.1.1 because you will choose a router ID and they will be unique for your routers. And the other one has 10.1.1.2. It's going to say, you know what? You have the lower number and I'm going to prefer you. So by the time it's said and done, if you reach this far down on the route selection criteria, it just resorts to random chance. So just like this killer frog, has certain attributes that helps him perform well in the EverQuest game. So each one of our BGP routes, every single one of them, will have a series of attributes that we just talked about that really helps your router choose the best way and the best route to get around the network. It gives you as the administrator ultimate customizability with how your router performs and chooses the routes to get around the internet. Now you can see just by going through each one of those attributes, there's a lot of administrative overhead that goes into choosing each route, especially when you consider the internet routing table has hundreds of thousands of routes that are in there. You are not going to sit down and choose each and every one. You're going to group them together and maybe choose one or two or just a few specific routes that you want to prefer from certain service providers. So when we went through this nugget, what we saw was all of those attributes, and then finally the route selection criteria that puts each one of them in a priority list. I hope this has been informative for you, and I'd like to thank you for viewing.